The Earth's atmosphere is unique in the sense that we have a well-controlled greenhouse effect. If we had a very thin atmosphere, the molecules would all be at a similar temperature because they're well mixed and the energy is being distributed across a thin layer. And if that's the case, any of the atmospheric molecules will be emitting the same amount of energy in all directions. The ones close to the surface of the Earth, as well as the ones at the top of this thin atmospheric layer. And so, proportionally speaking, quite a lot of the energy will be re-radiated back into space quite quickly. But when you've got a very deep atmosphere and you've got temperature gradients, like I showed in an earlier slide, things change a little bit. Now the gas or the particle close to the surface of the Earth is a lot warmer than the one that is up in the stratosphere or higher. And so the amount of energy that's being re-radiated by the very cold, high up molecule is quite small. And the percent of it that is being radiated upwards into space is even smaller. And so we get a blanket that protects or keeps the heat contained in the atmosphere. Now, it doesn't keep it there forever, but what it does do is it delays the length of time it takes for the heat to make it out, or for the energy to make it out into space. And that is a normal greenhouse effect. When we have a very thin atmosphere, the temperature of the Earth is estimated to have been about -6 degrees centigrade. In actual fact, our surface temperature is 15 degrees centigrade in about 2015. 15 degrees centigrade. That is 9 degrees warmer. And it's just because we have a nice deep atmosphere, and that moderates the amount of energy that's been lost and keeps the heat in our system for a little bit longer. Now, if we pull this all together, we can now develop an accurate representation of the components of radiation in our Earth atmosphere system. In this diagram, the numbers are represented as watts per square meter, and we have the situation we expected during the Holocene, when the climate was pretty constant. Around about 342 watts per square meter of shortwave energy entered the top of the atmosphere, and about only half of it makes it down to the surface of the Earth where it's absorbed. The rest is reflected and absorbed by the atmosphere. Of the absorbed radiation, the surface warms up and we get in the re-emittance of long wave, and eventually around about 390 watts per square meter gets shuffled back up through the atmosphere, of which 235 watts per square meter eventually make it back out into space. So when you have a look at all of these components, and you'll see we've included latent heat, we've included thermals from very hot surfaces, we've included sensible heat. When we look at it in its entirety, the incoming 342 is actually equal to the outgoing reflected 107 plus the outgoing long wave radiation 235. And this difference between incoming and the final amount that leaves the Earth atmosphere system, we call that radiative forcing. And so the net radiative forcing is 0 as long as we average over a year.